The quadratic equation is easy to solve but sufficiently complicated that we can use it to describe the energetic stability of chemical bonds and to find the pure frequencies of oscillation of coupled springs and masses. We graphically illustrate the meaning of solving the equation ax squared plus bx plus c equals 0 and then walk through an analytic derivation of the well-known quadratic formula. C corresponds to a horizontal bar. If C is non-zero, the red bar shifts vertically away from the x-axis. If the coefficient b is non-zero, the term bx is a slanted line passing through the origin where x equals y equals 0. The slanted line corresponding to bx is added to the constant c. If the coefficient a is non-zero, x squared becomes larger in magnitude as x increases and moves farther and farther to the right of x equals 0, as well as when x decreases and moves farther and farther to the left of x equals 0. Adding the term ax squared to the sum of bx plus c that we previously plotted produces another bowl-shaped curve. The sign of c determines whether the red dashed line floats above or below the origin. The sign of the coefficient b determines whether the slanted golden line ascends or descends to the right, and the sign of the coefficient a determines whether the blue curve opens upward or downward. In this cartoon, the quadratic curve y sub quad on x versus x intersects the horizontal line y sub 0 on x equals 0 at two locations. Solving ax squared plus bx plus c equals 0 means finding the values of x where the blue curve, which is ax squared plus bx plus c, is equal in height to y sub 0 on x equals 0, which is the x-axis. The values of x highlighted by the magnifying glasses are called roots or zeros of the quadratic function. One way to find these roots analytically in terms of a, b, and c is as follows. Assuming that a is non-zero, divide both sides of the equation by a. Dividing 0 by a simply gives back 0. We copy the preceding equation without doing anything. And continuing to do nothing, so to speak, we add and subtract to the left-hand side of the equation the same quantity, namely, numerator b over denominator 2a, the entire fraction squared. We use yellow highlighting to group the leading term x squared, the linear term bx over a, and the version of the constant that has the plus sign that we just added. The yellow terms are equivalent to a square of a sum, namely x plus b over 2a. The strategy of adding and subtracting b over 2a, quantity squared, in order to be able to reveal the square of the sum is called completing the square. When I next say go, please pause the video to verify that completing the square works. This is also a good time to check that you are comfortable with the term formatted in white font, namely the square root nested inside the square. Ready, go. We separate the difference of squares into two factors that produce 0 when multiplied together. The factors are identical except for a minus or plus sign between the portion in yellow parentheses and the portion in a white radical. The product is 0 if either factor is 0, which is abbreviated using a minus plus sign. Move the yellow b over 2a and the radical to the right. Write the expression out over a single denominator 2a to obtain the usual form of the quadratic formula. If the function whose association rule is y sub quad on x equals ax squared plus bx plus c, if that function intersects the x-axis at 2 points, we can use the quadratic formula to find those roots.